Muy bien, vamos entonces a continuar con la opinión de el otro de los referentes que fueron consultados, que es el doctor Bruce Golden. El doctor Bruce Golden es Bachelor of Science y Master of Science de la Universidad Estatal de Washington, tiene un PhD en genética y reproducción en la Universidad de Colorado, fue profesor de genética y reproducción en la misma universidad donde fundó el Centro de Evaluación Genética de Ganado y también en la Universidad Politécnica Estatal de California. Es cofundador y CEO de Data Solutions, compañía de servicios y software bioinformáticos especializada en análisis genético y genómico. Así que ya vamos a escuchar la opinión del doctor Golden sobre estas mismas preguntas.
Hello, my name is Bruce Golden, and I'm a managing partner and co-founder at Theta Solutions. I've been asked to discuss 5 questions about genomic data and its utilization in national animal evaluation. But before I do, I want to talk a little bit about our team and who Theta Solutions is. The company consists of 3 principals: myself, Dorian Garrick, who many of you may know from animal breeding, and Daniel Garrick, who is Dorian's son and joined the company in January of 2017. Our primary business is the licensing of software for performing large-scale, high-performance statistical analyses such as genetic evaluation, but also the curation and management of genomic data. The first question I've been asked to answer is, what are the advantages of genomic evaluation and selection in beef cattle? Well, that's very straightforward. There's really only one advantage, and that's in a substantial increase in accuracy can be achieved, especially for young animals when they're genotyped. This is particularly important for expensive to measure traits such as carcass traits or feed consumption. And it's also important for traits that are measured late in life, such as sustained cow fertility, stayability, longevity. Additionally, milk as a component of weaning weight is measured relatively late in life too, and the accuracy of milk predictions can go up as long as we get genotyped females. The second question I've been asked to address is, with the use of high-density chips for genomic prediction, will we get to a point where there will be no further need to record phenotypes? I'd answer that with a strong no. We will always need to record phenotypes. Genomic information allows us to squeeze more information out of the phenotypes that we do record, but it can't replace the phenotypes. And for a series of relatively complex reasons, these genomic predictions still suffer from error due to things that happen biologically and over time in these animals. Additionally, the genomic information that we have now doesn't account for all the genetic effect that an animal's genes have on its traits. There's a large proportion of genomic effect that can't be counted for by current markers. We call this the extrapolygenic effect. This slide illustrates that. What you're looking at is about 2,500 markers that we drew from a set of 50,000 markers where we looked for their impact on birth weight on the horizontal axis, post-weaning gain on the vertical axis, or both traits simultaneously. What's really interesting here is of these 2,500 markers, a substantial number of them had no effect on birth weight, but did affect post-weaning gain. Others had an effect on birth weight, but no effect on post-weaning gain. And then another set, a handful, had an effect on both traits simultaneously. We also know that the total amount of effect that these markers described only described a half or less of the total genetic effects that we see in cattle. The third question is it important to migrate from STR to SNPs for parentage verification? The answer is yes, it is. But it's really a question of numbers. STR has pretty limited amounts of data that it uses for parentage verification, where SNPs, you can use thousands or tens of thousands of markers to really be sure that you verified or refuted parentage. What happens in STR, and also in some of the SNP parentage panels where they use insufficient numbers of SNPs, is that they fail to reject a parent-offspring pair to verify, and they accept it. But then we've seen with some of our customers, when they take those same animals and go to the larger panels, up to 50,000, it's clear that they should have rejected that parentage verification. They accepted with the smaller amounts of data. The fourth question is, will genomic predictions from one country's genetic evaluation program work well in another country for the same breed? Generally, yes, but it depends. You have to be careful that you're measuring the traits that are truly the same in all countries. And we know that, especially for carcass traits, that there are some differences in the way animals are developed, and it may not be the exact same trait. But we can account for these sorts of things in our statistical procedures. But generally, EPDs produced, for example, in Hereford cattle in the United States, can be used successfully to make selection decisions in South America and vice versa. The fifth question is, what is the extra accuracy obtained from an animal with a genotype? Well, this varies by trait. It also varies given whether the animal is a parent or a non-parent, and the total amount of data available, and the total amount of genotyped animals. This slide illustrates that point. Along the left axis, the horizontal axis, is the prediction error variance of predictions. Now you can think of this as the inverse of accuracy. Prediction error variance is used to calculate accuracy. And for predictions with a low prediction error variance, they have very high accuracy. You can think AI sires. When the prediction error variance is high, that's low accuracy. And those are animals who are very young and have no progeny on their own. What I've done is along the horizontal axis, I've taken the prediction error variance from a traditional best linear unbiased prediction, a BLUP, where there was no genomic information used. And I took all the genotyped animals from that BLUP and averaged their prediction error variance and categorized them into 10 different groups. Way over here on the left, you can see these would be the AI sires, very low prediction error variance from the BLUP. And way over here on the right are all the young animals. They have the highest prediction error variance from a traditional BLUP analysis with no genomic data. The three lines then represent the prediction error variances for the BLUPs, and then the two lines below it are prediction error variances from two different analyses used to calculate, produce EPDs using genomic information. This middle line is a traditional model used by many organizations, and the lower line is the model that we use called a super hybrid model. What's important here is you can see for the young animals on the right side here, there's a nice gain in accuracy. The prediction error variance goes down when the genomic information is included. On the left side, there's not really much of a gain, especially for the highest accuracy animals. Another way to look at it is in this table, I've taken and I've averaged the accuracy for this set of traits on the left: birth weight, weaning weight, yearling weight, milk, calving ease, and sustained cow fertility for the 2016 born Hereford calves who were not genotyped and who were genotyped. And you can see the genotyped animals have a pretty substantial increase in prediction accuracy. So for all traits except for milk, in this evaluation at the time this was done, we had insufficient numbers of genotyped dams to really utilize genomic information. That is changing. We're getting a lot more genotype data. We have over double what we had when we started this evaluation.